Welcome to The Explainer. Today we're unpacking a really radical new theoretical framework. It's called Generating in the Limit with Infinitely Many Hallucinations. Now, if you spend your days thinking about AI, building models, or just trying to figure out why large language models do the weird things they do, you know that the word hallucination is basically treated like a dirty word. But what if the way we've been looking at this entire problem is just fundamentally mathematically flawed? Today, we're breaking down a fascinating new approach that shifts literally everything we thought we knew about language generation. Think about that for a second. What if AI hallucinations aren't bugs at all, but necessary features? I mean, for years, the entire AI industry has operated on this core assumption that any hallucination, any factual error, any fabricated string of text is an absolute total failure of the model. We've built massive infrastructure to detect them, filter them, and severely punish models for making them. But the source material we're looking at today challenges that traditional view head-on. We're going to explore a paradigm shift that suggests demanding zero hallucinations might actually be mathematically crippling our model's true potential. So here's our game plan for today. We'll start with the hallucination problem, move into a radical new framework, break down the precision recall trade-off, look at relaxing the rules, and finally cover some practical developer next steps. All right, part 1, the hallucination problem, and defining our current status quo. To really grasp where we're going, we first have to ground ourselves in how the industry currently views and categorizes this whole issue. Right now, hallucination is public enemy number 1 in generative AI. And to see just how deeply entrenched this view is, you can look at the AAAI 2025 tutorial on hallucinations in large multimodal models. The academic community puts these errors into highly specific buckets, giving them names like the factual mirage and the silver lining. The industry relies heavily on exhaustive benchmarking, detection, and mitigation to stamp these out completely. And as that tutorial points out, it's getting even trickier with multimodal models, because vision language models can actually exacerbate the problem by blending hallucinated text with misleading images. Right now, the entire focus is on fixing and eliminating these errors through black box and gray box methods. The ultimate goal? Zero hallucinations. Moving on to part 2, a radical new framework and the paradigm shift it brings. Okay, let's dive into this because this is where conventional wisdom gets flipped completely upside down. What actually happens if we step back from all the engineering duct tape and just look at the pure theoretical mathematics of language generation? Well, you get this groundbreaking paper, Generating in the Limit with Infinitely Many Hallucinations. This was submitted to Archive in June 2026 by researchers Irene Strauss, Alexandra Boutois, and Ryan Cotterell. I mean, just the title alone is provocative, right? Infinitely Many Hallucinations. They're proposing a formal model where learners are actually allowed to output infinitely many invalid strings. This isn't just some wild thought experiment. It's a rigorous mathematical framework that completely rethinks the theoretical constraints of language modeling. There's a massive, fundamental contrast between the old and new ways of modeling learning here. The classic paradigm is language identification in the limit. Think of that old model like a game between an adversary who reveals strings from an unknown target language and a learner who just has to recognize or identify them. But this new framework shifts the goalposts to language generation in the limit. And that better reflects modern LLMs because the learner's objective is now to actively produce valid, unseen strings from the target language. It's not just about recognizing data anymore. It's about actively generating it under strict constraints of enumeration, novelty, and validity. Which brings us to section 3, the precision recall trade-off. Let's look at the actual mechanics of this. So there is a fundamental mathematical tension when you ask a model to generate this unseen data. In traditional models, we enforce a strict validity constraint. We basically say, hey, every single thing you generate must be valid. The impact? It forces a zero error rate, sure, but it mathematically caps and degrades your recall. When an adversary or, in the real world, a proprietary dataset or restricted domain partially withholds the target language, demanding absolute validity actually harms the AI's ability to cover the target space. But with relaxed validity, the game completely changes. By allowing a vanishing frequency of errors, the model can actually maximize recall of that hidden data. Basically, broad coverage of a target language inherently conflicts with strict validity. You can't have both perfectly. The real trap here is this number. 100%. Forcing a strict 100% novelty and validity constraint is a dead end. If you force an AI to only produce 100% valid, unseen outputs, you're going to degrade its overall long-term performance. Why? Because the model eventually just exhausts its output budget. It gets stuck. It's kind of like writer's block for AI.
It needs room to breathe, to make occasional repetitions or errors in order to maintain broad, sweeping coverage of the target language.
Section 4. Relaxing the rules. Let's dig into the theory's mechanics.
So how do Strauss, Botoy, and Cotterell mathematically justify dropping these standard rules? They do it by targeting zero. And by that, I mean the frequency of errors. The standard theoretical requirement has always been that a learner must be eventually valid, meaning after a finite number of steps, it just magically converges to producing 100% valid outputs forever. This paper says, scratch that. They mathematically prove that we can allow a model to make infinitely many mistakes, provided that the statistical frequency of these errors approaches zero over time. As long as the ratio of invalid outputs to total outputs decays towards zero, the formal precision of the model remains at 1. This is the massive aha moment of the whole paper. Hallucination is a tunable statistical rate, not a binary pass or fail bug. If you withhold a large portion of the data, strict validity causes recall to just collapse. But this relaxed model recovers that coverage by permitting early-stage errors. As the AI explores and enumerates more of the target space, those errors naturally diminish over time. And honestly, this aligns perfectly with what we actually see in real production LLMs. Occasionally, hallucinations are simply unavoidable. But if the rate is bounded and controlled, it's completely acceptable for downstream consumption.
All right, our final part, Section 5, Practical Developer Next Steps. Let's take this theory and see how it lands in reality. So if hallucination is a rate and not just a binary fail, how should development teams and researchers actually change what they're doing right now? The implications here are heavily architectural. Step 1. You need to replace your binary validity checks, those simple pass-fail tests, with frequency-based metrics. Step 2. Start tracking the decay rate of invalid outputs over rolling windows. Stop just asking, did it hallucinate? And start asking, is the rate of hallucination decaying appropriately over time? And step 3. Measure precision dynamically. The formula the paper suggests is 1 minus the ratio of invalid outputs to total outputs, and you've got to monitor how that converges over generation steps.
You've also got to seriously rethink your sampling parameters. You should be treating temperature, top P, and repetition penalties as coupled controls for balancing novelty and validity. Because this continuous novelty relaxation proves that forcing 100% novelty degrades recall, you should set a fixed novelty fraction in your evaluation harness instead. Adjust those sampling parameters to maintain your target error frequency decay. And hey, if you're dealing with permanently withheld data, like when you're fine-tuning on a highly restricted domain, you absolutely must plot precision recall curves. This is going to reveal that sweet spot, the optimal operating point, where your required coverage meets an acceptable hallucination rate.
This also totally changes how we need to build guardrails. For formal verification layers and schema validators, we have to shift away from hard rejection to rate-limiting buffers. Right now, if an output fails a schema check, validation layers typically just reject it outright. Boom, done. But under this new theoretical bound, you should actually allow outputs that fail validation to pass through into a controlled buffer, and then measure the decay rate. If that rate successfully approaches zero, the model has converged.
To really wrap your head around this entire shift, we can look right at the abstract of the archive paper itself. They say, occasional errors and repetitions are unavoidable, but their rates are controlled. By stepping away from the mathematical fantasy of perfect, error-free enumeration, we move toward a much more realistic, statistically controlled model of language generation. We are basically trading an artificial, mathematical ceiling on recall for a bounded, totally manageable rate of hallucination. It completely changes the way we should define and evaluate success in generative AI. So I'll leave you with this final thought. If demanding perfect accuracy mathematically limits your model's potential coverage and recall, how many controlled errors will you allow in your next model? Thanks for joining me for this explainer, and I really hope this helps you look at your own AI guardrails and validation systems in a whole new light. Catch you next time.